So we're bringing all of this together with limits and the idea of this instantaneous rate of change, this idea of being tangent to that curve. We're bringing it all together with this idea of what we call the difference quotient. Difference meaning subtraction between two things, and a quotient as in division. So we're going to talk about that for a second. So we've been talking about your average rate of change between these 2 points, that we draw a line between those 2 points and we say, okay, well that slope there is kind of representative of the average rate of change between those two x values. And so we're going to kind of do the same thing here by looking at a point right here when compared to an average point that could be anywhere, not an average point, maybe an example point that could be anywhere on the curve. So notice that this is a curve of x squared. So the x value of that coordinate is x, and then the y value of that coordinate is what the definition of that function is, which is x squared. So we're just saying pretty much x f of x in that point right there. And then we've got another point that we know is on the curve, and we say that point is 1, 1. So if I wanted to find the average rate of change between those 2 points, I would find my slope by finding my change in my y values over my change in my x values. So I would take x squared as my y value right here and subtract out the y value over here, which is 1, over my x value, which is x, minus my x value over here, which is 1. And so if I wanted to find the average rate of change, notice that when I don't have 2 points and instead have only 1 point and then an example of any other point that could be on this curve, that I end up getting a different equation, an equation that's different than my original one of x squared. Kind of strange. So if I wanted to figure out, well, what is the average rate of change, I can kind of simplify this a little bit if I wanted to. Remember, difference of two perfect squares, x squared minus 1 factors into x plus 1 times x minus 1. If you remember that, awesome. If not, don't freak out about it. It's totally fine. And you've got x minus 1 on the bottom, and you've got in the denominator, you've got x minus 1 in the numerator, so they both cancel out, and it could technically simplify down to x plus 1. But as we talked about in our very first problem on the other page, that while it does simplify down to this x plus 1, keep in mind the domain restriction that you can't actually have 1 in the denominator. So then when we ask ourselves, well, what's the instantaneous? It's a hard word. Instantaneous rate of change. As x approaches 1, what's happening? What's the instantaneous rate of change at 1? We can think of the idea of this equation as a limit. Well, what's happening is that since this is any point on the graph, I could take any other point and say this is the average rate of change. If I took 0, 0 and said what's the average rate of change between the origin and this point, then I could just plug it into this formula and get that average rate of change given any point. So then the idea of your instantaneous rate of change is actually as that point gets closer and closer to the same point as what we used. So what happens as that point gets here, and what happens to that line? And what happens as that point moves up here and gets closer to that tangent line? And we're saying, hey, well, actually what we're doing is we're finding the limit of this average rate of change as this random point that could be anywhere on the graph is getting closer and closer and closer and closer to the point we're actually trying to find where that instantaneous rate of change is. So we show it as the limit as x approaches 1, so trying to figure out what is the slope, the instantaneous rate of change at 1. The limit is x approaches 1 of this function, x squared minus 1 over x minus 1. So thinking back to our domain restriction of, well, it's pretty much kind of like x plus 1. It simplifies down to that. But what's happening is that you have a domain restriction where x cannot equal 1, because if you plugged in 1 for x, you'd have a 0 in denominator, and everybody freaks out, and so we don't do it, right? But if we said, okay, we understand that this is, graphing this on the calculator, getting rid of this table. Getting rid of other graphs. Plugging in this equation, it looks like a line because, hey, it simplifies down to pretty much a line, except for this one domain restriction. If I typed in tracing my graph, what's happening at 1, it's undefined. So as we talked about in class, the limit doesn't care what's actually happening at 1. Yes, it's undefined there, but we're saying what's happening as we get closer to 1, approaching it from the left-hand side and then approaching it from the right-hand side. So we can kind of scroll over a little bit and see like, okay, well, it's kind of like 0.7 and then 1.7 as my y value, undefined, and then 2.3 on the other side. Maybe I don't have enough information. You could always, if you wanted to, this is how you do it. You hit table, and if you split screen table, you create this table on the other side where you have an x value of 1 and it's undefined. You can scroll up and see what's happening at 0, 1, 2, 3, and sometimes I'm like, oh, I want to know what's going on closer to that. So you can change your menu settings. If you go to menu, table, edit table settings, your table start, if I'm trying to focus on what's happening as x approaches 1, I want my table to be oriented around the x value of 1. So I plug in 1 there. Table setup, if I want to, step, if I want to have numbers that are much closer, I could have a step of 0.1. And then now notice that the numbers on this table are 0.9, 1, 1.1. So we're stepping by that 0.1 value. I could go back and I could change that and get even closer zoomed in on 1, where I have a table start at 1, where I want my limit to go to, and a step of 0.01. Now I'm getting a little bit closer. And now it's a little bit easier to see, as we talked about in class, from a table, what is that limit? Well, that limit, as we're approaching 1, is 2. Which, hey, if you notice, if we're trying to do this algebraically, sometimes with limits, you can just plug in the number into the equation. 1 plus 1 is 2. Sometimes it works out that way, not always, as we saw with the infinity in class. It gets a little strange, but that is the instantaneous rate of change at this graph at point 1. That we're taking this idea of the average rate of change and finding the limit as this generic point, x, f of x, gets closer and closer and closer to where you want to find that slope. So if we wanted to try it again and try it in a different perspective, finding the gradient of that guy, the slope would look, the graph would look something like this. And we're trying to find out what is the gradient at 0. X value 0, if you plugged in 0 for x, you would get what? 2 to the x, 2 to the 0, anything to the 0 is 1. So that point actually becomes 0, 1. And then if we're talking about this idea of an instantaneous rate of change, we're talking about the limit as your average rate of change gets closer and closer and closer to be the same point. So I could just pick any point on the graph and label it x, and then f of x, as we talked about up here, or we could label it as the equation, x, comma, 2 to the x. So this is your input, and then your output would, of course, be the function that gives you your output. So now we have this information, so we can talk about the average rate of change. And your average rate of change is your difference in your x values, your difference in your y values over the difference in your x values. So that would be your average between any between any one point and this point right here, 0, 1. If I wanted to talk about the instantaneous, we're talking about the limit as x approaches 0, the point where we want to have that slope of this equation. Notice plugging in 0 just straight into this equation is not going to work because it creates a 0 in the denominator and alarm bells sound. So we can use our calculator. If you press menu, table, you can remove the table for now so you can have a look at this whole graph. You can go back in and you can regraph it. 2 to the x minus 1 divided by x, and it looks something like that. So if I wanted to trace this guy and go to 0, it's going to be undefined, right? So I can go a little bit to the left and get some information, go a little bit to the right and get some information, but I don't know exactly what that number is. So we can use our table again to get a better idea. Table, split screen table. I want to know what's going on at 0. I can see undefined at 0. So I want to change my step to make sure that I'm a little bit further zoomed in, as we saw in class today. Table settings, starting at 0, and I'll have my step be 0.01. Here it's a little bit easier to see what number is going to be squeezed in between these two values. That we're at 0.69075 and then 0.69555. Notice that both of these would, this one would round to 0.691, 0.696. So I think I might want to zoom in a little bit more because they won't round to the same 3 significant figures. My last digit here would be 1 versus my last digit here would be 6. So I think I want to step in just a little bit more to get a better idea. So I'm going to start at 0, and instead of 0.01, I'm going to do 0.001. And now it's a little bit easier to see what it would round to, because 3 sig figs would round to the same thing, a little bit below and a little bit above. They would round to 0.693 for both of them. And that is a way that you can kind of use your calculator as well as what you know about limits and tangent lines and slopes all used together. Calculus is where we see it all coming together, which is a beautiful thing. 0.693. Great job.